topic today is section 10.7, the wave equation. So we're going to look at vibrations of an elastic string. So you're going to see a lot of similarities here. So with what we've done before, but we're going to start with one. And this equation is going to be a squared, the second partial derivative with respect to x of u is equal to the second partial derivative with respect to t. So a slight change from before. Whenever we dealt with the heat conduction, it was only the first derivative on the right hand side. And for this, we want our x to be between 0 and L, whatever the length of that string is, and t is going to be greater than 0. So to draw a picture of this is where x equals 0. Let me make that an actual x. And out here is where x equals L. And then we're going to have the wave vibrating. And this height here is going to be u of both x and t. Now this a, actually the a squared, is going to be t over rho. Now our t is going to be tension. The force in the string. Our rho is going to be the mass per unit length of the string. As a guy with the leaf blower outside. Now for A, these units are going to be length divided by time. Now that's for A, so it's a velocity, but it's A squared, so it's a velocity squared. And now with this, we're going to have boundary conditions. And that would mean that the ends of the string are anchored. They are firmly attached to whatever it is we have, so that we know that the ends of the string will not move at all. So that means that our u at 0t is going to equal 0, and our u at L and t will also equal 0. So no matter what time we have at 0 and at L, the ends of the string, they're always going to be right there in the middle. And this will be for any t greater than or equal to 0. But we're also going to need initial conditions. So our initial conditions, now that we don't have the leaf blower anymore, are that for our u at time 0 for whatever x, we'll call that some f of x, and that will be for our x between 0 and L, and that will be position. And then we'll have our u, and actually let me write this, our derivative, but it's going to be derivative with respect to t of x 0 which we'll call g of x. And that will be velocity. And for both of these, x is between 0 and L. So we've now taken our initial conditions and made them both functions of x because we don't need to worry about the t anymore. So we're going to go through our couple of different situations depending on all of our different details. So the first one is elastic string with a non-zero initial displacement. So the initial displacement, initial position is not zero. So our string has already been pulled somewhere. It's pulled in some way, shape, or how. It's not just sitting there whenever we start, or it's not passing through the equilibrium. So for this, as before, our initial condition, some f of x, and then our derivative with respect to t will be g of x. And so if we continue on there, if we do that, that'll be f of 0, which is going to be 0 because that's our left endpoint. If we plug in an L, that's also 0. So since we have our non-zero displacement, our string is pulled, but it's held there, and then we start our clock as soon as we let go. So our initial velocity is going to be 0. Now, in order to solve this, we're going to do what we did before of taking our u and writing it as a separable equation. So whenever we do our equation we had set up from before, it's going to look like that. So now whenever we group things together and make it separable, straight lines, and then this whole thing is going to equal some negative lambda. And this negative lambda is going to be called the separation constant, just like we had before. So now we're going to be able to rewrite these equations with our lambda. And with our initial conditions and our boundary conditions, we get those. And our results are going to be very similar to what we had with our heat conduction. So our lambda equals n squared pi squared L squared. Let me erase this line so it's not cutting through what I'm writing. There we go. And this is going to be for our n's that are natural numbers. So 1, 2, 3, 4, 5, 6 positive whole numbers. And our x equation is going to be some c times sine of n pi x over L. So with these lambdas, this can be our eigenvalue, and then that's going to be our eigenfunction. So we get a non-trivial setup. So if we use this lambda to find our t, our t value comes out to be and just to make that a little bit clearer, that should be an A right in there. So n pi AT over L for both. So with our initial conditions that we had up here, our K2 is going to be 0. So we have to reduce our solution down to there. So writing this all together for our U equation, we end up n, to depend on our n value, sine n pi x over L times cosine n pi a t over L. And again, it's for n's that are natural numbers. Of course, that gives us our fundamental set of solutions. When we combine it all together into our big equation, we need to introduce our coefficients out front. So make my ends look like ends, not H's. And just like what we did before, if we make our t 0, then this whole part is going to become just a 1. So there's our f of x. Then we can use this to find our c sub n. Again, this will be for n's that are natural numbers. So a lot of similarity with what we had before. Let me clean this up, make that not so run together. There we go. Now we have what's called a natural frequency. This will be the n pi a over L, where n is a natural number. And to make that better. So this is going to be the frequency vibrates. Try to put that on one line. So if we just pull the string, let it go, that's going to be our frequency with no interference. The natural mode is going to be the displacement pattern resulting from this sine of n pi x over L at frequency. And you can see this will be periodic based on our x variable. So it'll be periodic in the space variable x is the way it would be said. And now last thing before we move on to another example is the wavelength of mode of frequency n pi a over L is going to be 2L over n. So if you look at that wavelength, essentially the period is 2 pi over whoops, except for we don't put the x in there. So if we do our canceling and move things around, you can see you get that 2L over n. So next, actually, let's go back. So oops, this should not be there. That should be a 0. There we go. So whenever an elastic string non-zero velocity. So now our string, we pulled our string, we let it go, but it's sometime after we've let it go that we start our clock to say here's where time equals 0. Just like before. We're going to use the same zero and L, same equation as what we did before. T will be greater than 0. And here we're still going to have that our U at 0 is equal to the U at L, no matter what the time is. And we're going to start it at some point whenever we're going through the equilibrium point. So we want, no matter where it's at time 0, we have a straight flat string, but it's moving through that equilibrium spot. And the derivative with respect to x at 0 is a g of x. And for all these, x will be 0 and L inclusive. So, like before, we're going to have an eigenvalue of n squared pi squared over L squared. Or n being natural numbers. And we're going to get the exact same results, just different. So our x is going to be something times our sine of n pi x over L. And now our t of 0 is 0. So we have a different initial condition that we're building off of. So our t, even though it's written as a sine plus a cosine in general, based on our initial conditions, our k1 this time has to be a 0, so we have no more cosine portion. So going back, we still have this equation. This time, we're going to get rid of the cosine and we're going to keep the sine. So combining everything together, for any n value as part of our fundamental set, we have that. And then if we find our overall u, and we have to include the constants in this, which we're making a general solution. And they use k for this. Doesn't really make much difference what we call our variable. That's going to be times our u. So it's going to be a sine and another sine. So now if we take our derivative with respect to t, oh, you got space up here. And then we plug in 0 for our time. When we take this derivative, it's a partial with respect to t. So all of this is treated as a constant. And then this, when we take the derivative, turns into a cosine. Then a cosine of 0 is going to be just 1. And that it's not writing properly. Come on, erase. There we go. And now we're doing the derivative with the table built into there. We get an n pi a over L, case of n, sine of n pi x over L, which is going to be our g of x equation. So whenever we solve for our case of n, with this equation, we can then clear off that n pi a over L, and we're multiplied by 2 over L, so those L's will cancel. And there's your tx built in, thrown in there. Let me rewrite that so it's a little bit better, and rewrite that 0. Just squeeze that in there. And this will be for all n's that are natural numbers. So now with the general equation, general problem for elastic string. So this one, we don't necessarily have a nice setup where either our initial starting point is right at equilibrium or our initial velocity is 0. Now we might have pulled the string and let go, and it's not quite equilibrium, but it's moving, and we start our clock. So we have an initial position and an initial velocity, and we're going to have to deal with both of those. As before, and we have our endpoints anchored as usual. And that's for t greater than 0. Our initial position will be given that. Our initial velocity is there. And for this one, our x is between 0 and L. Let me make those look a little bit better. I noticed a little bit of a difference in this from what we did before, is that our endpoints are not included. It really doesn't make much difference because we already know that our endpoints, whenever our x equals L or 0, we have 0 anyway. And we also know that those endpoints are not going to move. So the derivatives are always 0. But now if we get our solution for this, interesting enough, it's going to be just the summation of our two previous solutions. So whenever we had our non-zero initial position and our non-zero initial velocity. So the book breaks it up into two separate summations. Let me up a bit. Plus and let me close out that big parenthesis at the end. But this is an example of using the principle of superposition. So we can then expand this whole idea to two-dimensional and three-dimensional wave equations. So for this, it's going to be a squared times second derivative with respect to x plus second derivative with respect to y. We have more dimensions to deal with. And then our u is going to be a function of x, y, and t. And with our three dimensions, as you probably guessed it, so we just have to use our z axis in here. So some things that will work with our two-dimensional, or where we can use it, will be waves in an ocean. So not only does it have up and down, but it also has that length going with it. And the waves are still pretty much moving in one direction though. You can also have acoustical waves in the atmosphere. You can have electromagnetic waves in the atmosphere or elastic waves in a solid body. Our three-dimensional one is motion of a thin elastic sheet. So kind of like a drum head. So that is the general idea of expanding it, where it's just more dimensions we have to deal with, but it's going to be the same general idea.